Hi, I'm Mingda Qiao. In this video, I will be presenting our paper on a combinatorial approach to robust PCA, which is joint work with Weihao and Rajat from Google Research. So the following is a typical pipeline for robust statistics. At first, a clean data set is drawn, and each data point follows some underlying data distribution independently. Then, an adversary examines this data set and replaces a small fraction of the data points arbitrarily. Our algorithm only has access to this corrupted data set and wants to recover some property of the underlying data distribution. The implicit assumption in this model is that each data point is an atomic object. So each data point is either entirely clean or completely under the control of the adversary in the final corrupted dataset. In some scenarios, this modeling assumption is not too realistic. So suppose that each xi is an image that lies in very high dimensions. And it's conceivable that in the actual dataset, the data point is not completely corrupted, but a small fraction of it that's replaced by some adversary. So this motivates our study on a coordinate level model of corruptions. Concretely, in our model, each data point xi is a d-dimensional vector drawn from some unknown Gaussian distribution. The data are structured in the sense that the covariance matrix sigma is degenerate and has rank k much lower than d. The corruption model is as follows. First, the nature draws a random corruption set Si that consists of S randomly chosen coordinates out of the D coordinates. Then the adversary corrupts the data under the constraint that it can only replace the J's coordinate of Xi if J is inside the corruption set Si for that data point. In this model, we obtain the following result for recovering the dataset. Under the assumption that Ks squared is bounded by order D, there's an efficient algorithm that recovers each data point in the dataset up to an L1 error of bit O tilde BKS over D in expectation. So recall that K is the intrinsic dimensionality of the data, S is the number of corrupted entries per data point, and D is the ambient dimension. B is a scaling factor that depends on the magnitude of the covariance matrix. So a few remarks. First of all, it's relatively easy to show that we cannot beat this BKS over D error rate in general. So our error is nearly optimal up to a polynomial factor. Second, given this recovery result, we can post-process the recovered dataset and learn something about the underlying distribution. Concretely, we can estimate the mean vector mu up to an L1 error that satisfies the same error bound. And thirdly, given this mean estimation guarantee, it's natural to ask whether we can recover each coordinate of mu separately. We can verify that doing this naively will give an error that scales as B times S, which is much higher if K is much smaller than D. Another way to view our model and our result is through the lens of robust PCA, which is a problem of decomposing a matrix into a low-rank matrix plus a sparse matrix. There's been a long line of work on robust PCA, starting from a seminal work of Candice, Lee, Ma, and Wright. So to frame our result into robust PCA, we consider the data matrix whose columns are the data points. By our modeling assumption, this data matrix can be written as the sum of two matrices, where the first corresponds to the clean data, and the second corresponds to the additive corruptions. The first matrix must be low rank because each data point lies in a low dimensional subspace. The second matrix must be sparse because each column can only contain a few corrupted entries. Then our algorithm gives a way of recovering this decomposition approximately. The key step in our proof will be solving a sparse recovery problem. And in fact, the reduction from the original problem to sparse recovery is straightforward. So we will focus on sparse recovery in the rest of the video. In our setup of sparse recovery, there's some plain data vector X that lies in subspace U of R to the D of dimension K. So again, we should think of K as much smaller than D. Then the nature draws a random corruption set S as usual, and the adversary corrupts X into X tilde such that for every index I inside the set S, X tilde I and Xi can differ by at most 1. For every I outside S, the adversary cannot change Xi. Our goal is to recover the clean data vector X given X tilde and the subspace U. In the model that we defined on the previous slide, the corruption set S is chosen randomly, whereas in most formulations of sparse recovery, this set can be arbitrary. Here we state a simple fact that if we have no assumption on the choice of the corruption set S and no further assumptions of any kind, we cannot do any non-trivial recovery. This is true even if both K and S are much smaller than D. So recall that K is the dimensionality of the subspace and S is the number of corrupted entries. So when they are small, it should mean that the data is more structured and the adversary is weaker. But we show that even in this case, recovery is not possible. For the proof, we consider the subspace U consisting of all the vectors supported on the first K coordinates. Then we let the adversary pick S to be 1 through K and replace each Xi with Xi plus or minus 1 for every I in this corruption set S. So information theoretically, for the first K coordinates, we cannot recover any of them with an error better than 1 expectation. So the L1 error in our final recovery will be at least K. On the other hand, that's exactly the error we would obtain if we run the naive algorithm, which uses X tilde as the estimate for X. In this proof, the only reason for the adversary to succeed is that the locations of the corruptions are perfectly aligned with the informative entries in the data vector. And in our model, in our actual model, S is randomly chosen, so this first case will happen very unlikely. At a higher level, we can imagine this two-dimensional landscape of sparse recovery, where one axis corresponds to the amount of assumptions we made on subspace U, and the other corresponds to the assumptions on the corruption set S. We saw from the last slide, if there's no assumption of any kind, we can't do anything non-trivial. Most prior work on sparse recovery focused on the case that some structural assumptions like incoherence or restricted isometry property are imposed on subspace U. Under those cases, exact recovery is possible. In contrast, the focus of this work is a condition where subspace U is essentially arbitrary, but the corruption set S is randomly distributed. In part of this regime, we give the near optimal recovery guarantee. So this is our main theorem. It says when Ks squared is bit O of D, this is an efficient algorithm that recovers the clean data X up to an L1 error of bit O tilde Ks over D in expectation. This is achieved by a fairly straightforward algorithm for the basis pursuit or BP program that simply finds the vector X hat in subspace U that is closest to the corrupted version X tilde in L1 distance. Again, it's easy to see that this Ks over D error rate cannot be improved. Also, in our result, the expectation is only over the randomness in the corruption set S. So in other words, the theorem holds for arbitrary choice of the subspace U, the clean data X, and the adversary strategy for corrupting the data. To see how our theorem is proved, it's useful to start from the textbook approach to sparse recovery. So we have this observation that one obstacle towards sparse recovery is the existence of sparse vectors. So suppose the subspace U contains a vector little u that is S sparse, then we're in trouble, because suppose we are given the corrupted version X tilde being U. On one hand, it might be that the clean data is a zero vector, and the corruption happens to be on the support of U. It could also be that the clean data is U, and the adversary did nothing. So we cannot tell these two traces apart, so we can't do exact recovery. On the other hand, it is known that this is essentially the only obstacle towards sparse recovery. So formally, the textbook approach builds on this definition of restricted null space property, or SRNP. U satisfies SRNP if for any vector U that is non-zero in U, and any set S of size little s, we have this inequality, which states that the contribution of the coordinates with indices in S to the one norm of U is strictly less than 1/2 of the one norm of U. Then it is well known that under this SRNP condition, the basis pursuit program always recovers X exactly. The first step in our proof is to prove a quantitative version or extension of the textbook result. So we have this definition saying that a set S is T dominant with respect to the subspace U if we can find a vector little u with a unit one norm, and such that if we look at all the entries with indices in S, and we only count the ui whose absolute value is less than 1/t, the contribution of these coordinates to the one norm of u is at least half. Then we prove lemma 1, which is an analog of the textbook theorem. It says when BP incurs an L1 error of T, the corresponding corruption set S must be T dominant. So recall that the textbook theorem says that when BP is not perfect, SRNP must be violated. So the textbook theorem gives a necessary condition for BP to make any non-zero error. In contrast, our lemma 1 gives the necessary condition for BP to incur a high error, and this will be useful for controlling the expected error of BP. Now, given this lemma 1, we fix a subspace U and some parameter T, and consider the family F of all the T dominant sets with respect to the subspace U. Recall that we wanted to upper bound the expected error incurred by BP, so it's sufficient to bound the tail probability. By lemma 1, BP incurs error T only if the corruption set S is in the family F. And because S is randomly chosen, this probability is exactly the size of F divided by D choose S. So the crux of our proof is to upper bound the size of the family F. This is done in two steps. First, we show that the family satisfies a following combinatorial property, which roughly says that we can't find K sets in F that are almost disjoint. Let's call this property star. In the second step, we show that any set system satisfying property star must have a small size. So this second step is essentially a combinatorics problem, and indeed, we borrow some ideas from combinatorics. I'll sketch how the proof works for a special case. So now we redefine F to be the family of size S subsets, such that for some vector u in the subspace capital U, the contribution of the coordinates with indices in S to the one norm is strictly greater than 1/2 of the one norm. We can verify that this F is actually a subset of one dominant set of size S. So proving this special case does not give what we want, but the proof does capture the important ideas in the actual proof. Now, concretely, for this first step, we show that F cannot contain K+1 sets that are pairwise disjoint. In the second step, we show that this property implies the following cardinality bound on F. So when K and S are both small, this bound says that F constitutes a negligible fraction of all the size S subsets of 1 through D. For the first step, we give a proof by example. Let's say both S and K are equal to 2, and the ambient dimension D is 6. Suppose, for the sake of contradiction, that we can find K+1 sets or 3 sets in F that are pairwise disjoint. Let's say they are 1, 2, 3, 4, and 5, 6. By our definition of F, for each set, we can find a witness U. So, for example, for the first set 1, 2, we have this first row of the matrix such that the first two coordinates contribute at least 1/2 of the one norm of this row. we can do the same thing for the other two sets and obtain this 3x6 matrix. Given this matrix, we will carefully aggregate its columns appropriately and obtain a 3x3 matrix. So the first column of the new matrix is the sum of the first two columns of the original matrix. The second column is the difference between the third and the fourth, and the last column being the difference between the fifth and sixth. So the way we aggregate the columns is to make sure that the red entries, when they are added up, they give the maximal value. So we'll need to negate some of the columns beforehand. And by our construction of the new matrix, this new matrix must be diagonally dominant in the sense that each diagonal entry is strictly higher than the sum of the absolute values of the other entries in the same row. It's well known that such matrix must be full rank, so we obtain a rank k+1 matrix in this way. On the other hand, it's a fairly simple linear algebra exercise to show that the resulting matrix must have a rank upper bounded by the dimensionality of U, which is k. So this leads to a contradiction. In other words, we prove this property star. For the second step, we adapt a proof of Catona for the Erdős-Torrado theorem in extremal combinatorics. We first choose M to be D over S and consider M random sets A1 through AM that are all size S and pairwise disjoint. Then we examine the expected size of the intersection between F and A1 through AM. On one hand, this expectation is given by the size of F times M divided by D choose S by the linearity of expectation. This is because for every set in F, it coincides with some AI with probability 1 over D choose S. On the other hand, this expectation must be at most K, because for any realization of A1 through AM, F can contain at most K sets in them, because otherwise we would find K+1 sets in F that are pairwise disjoint, which contradicts property star. So combining these two facts and do some rearranging gives the desired upper bound on the size of F. Now to recap, in this work, we define a new model of robust statistics, where the data are high dimensional and the corrections happen on a coordinate level. Secondly, we give a new result for sparse recovery. It differs from the previous work in that it makes no assumption on the subspace U and only assumes that the corruptions happen at random locations. And finally, we build a new connection between sparse recovery and combinatorics. Concretely, in our paper, we stated a concrete conjecture in combinatorics that it would imply a better recovery guarantee for our problem. This is the end of the video. Thank you for watching.